So today, we're going to unpack one of the most powerful tools in industrial safety, the HAZOP study. For decades, it's been considered the absolute gold standard for preventing disasters in really complex plants. And we're about to find out exactly why.
I want you to just picture a massive chemical plant for a second. This sprawling, almost endless network of pipes and vessels and reactors. How in the world do you even begin to predict what could go wrong? The sheer complexity is a huge challenge, because the biggest danger isn't just one part breaking.
And see, that right there, that is the absolute core idea behind a HAZOP. It doesn't just ask, hey, is this valve going to fail? No. Instead, it asks a much smarter question. What happens if the flow through this pipe is suddenly way more than we designed for? It's a total shift in thinking, right? Moving away from just a single broken part to looking at the entire system's behavior.
So, to get our heads around all this, we'll start with what a HAZOP actually is. Then, we'll walk through the whole step-by-step process. We'll look at some of its modern variations, see how it stacks up against other safety tools, and finally, we'll peek into the future and see how AI is totally changing the game.
Okay, first up, what exactly is a HAZOP? Let's unpack why it's earned this reputation as the gold standard in the industry.
So, officially, HAZOP stands for Hazard and Operability Study. And honestly, the two most important words in that whole definition are systematic and structured. This is not just some casual brainstorming session where everyone throws ideas at a wall. It's a super rigorous, really methodical examination of a process from literally every angle you can think of.
And the name itself really tells you everything you need to know. It's built on two pillars. First, you have hazard. That's all about safety, finding anything that could potentially cause harm to people or the environment. But just as important as the other side, operability. This looks for all the things that could hurt production, cause downtime, or create annoying bottlenecks. So it's about being both safe and efficient.
And this is not some new fad. HAZOP was actually developed way back in the 1960s by Imperial Chemical Industries over in the UK. And since then, it's been polished and refined and eventually formalized into a global standard, IEC 61882. And that's a big deal, because it means a HAZOP done in one country is completely understood and trusted everywhere else in the world.
So that's the what, but how does it actually work in practice? Let's dive into the step-by-step process and see how this method actually uncovers all those hidden risks that can be so dangerous.
Okay, a HAZOP basically follows 5 key phases. You start by defining the scope and, crucially, getting the right people in the room. Then you take this massive complex system and you break it down into manageable chunks. They call them nodes. Phase 3, that's where the real magic happens. You apply these specific guide words. From there, you identify what could go wrong and why, and then finally, you look at your safety nets and make recommendations to make them stronger.
And that first phase, team formation, is totally non-negotiable. A HAZOP's success lives or dies based on the people involved. You absolutely need an objective facilitator, someone to write everything down, the engineer who knows the design inside and out, and, this is so important, the plant operator who knows how things actually work out there on the floor. It's that blend of book smarts and real-world experience that makes this whole thing so powerful.
Now, here it is. This is the creative engine of the whole HAZOP process. It's so simple, but it's brilliant. The team takes a process parameter, something like flow or temperature, and they just combine it with a simple guide word, like more, less, or reverse. This simple pairing forces them to systematically brainstorm every possible way the system could go off the rails. More flow, less temperature, reverse flow. It's a structured way to imagine the unimaginable. And this example just perfectly illustrates how it works. Let's take that deviation, high flow. The team asks, okay, what could cause that? Well, maybe a valve gets stuck open. And what's the consequence of that? A tank could overflow and spill everywhere. So what safeguards do we have? We have a high-level alarm. But then you ask the important question, is that really enough? Maybe not. So the recommendation is to add an automatic shutdown switch. You see, it's this complete logical chain from a potential problem all the way to a concrete solution.
But hey, HAZOP isn't a one-size-fits-all tool. The methodology has actually evolved over the years to tackle some very specific, very modern challenges.
For example, there's something called a Human HAZOP, which focuses specifically on human error. It analyzes things like cognitive load and the very real danger of alarm fatigue, where operators get bombarded with so many alerts that they just start tuning them out.
And of course, in our super automated world, there's CHAZOP, which applies that same logic to computer control systems, looking for failures in software and digital signals.
So, with all these different variations, you might be wondering, where does HAZOP fit into the bigger picture of safety analysis? Let's take a look at how it compares to some of the other common tools out there.
This chart lays it out perfectly. So you have hazard identification, which you do way early on just to spot the big picture risks. Then you have FMEA, which zooms way in on single component failures. But HAZOP, that occupies its own unique space. It gets applied during the detailed engineering phase, and its primary focus is on system deviations. What happens when the whole process starts acting in a way it's not supposed to? So let's be super clear on this, because it's the most important difference. FMEA asks what happens if this one pump motor breaks, but HAZOP asks a broader question. What happens if there's more flow in the entire system? Now that extra flow might be caused by a broken pump, sure, but it could also be caused by human error or a faulty sensor. FMEA is systemic. It looks at the whole picture. FMEA is component analytical. It looks at the individual parts.
And this is really important. A HAZOP is often just the beginning of the journey. Think of it like a big funnel that identifies all the things that could go wrong. And when it flags a really high-risk scenario, that usually triggers a more detailed quantitative study like a LOPA, or layer of protection analysis, to really dig in and make sure all your safety layers are strong enough to do their job.
All right, on to our final section. We've seen the past and the present of HAZOP, but what does the future hold? Well, it probably won't surprise you to hear that it involves a whole lot of AI.
This quote really captures the direction we're all headed. And notice the key word there is assisted. The goal isn't to replace the human element, but to augment it, to give it superpowers with these new tools.
And check this out. The data is pretty stunning. Recent research shows that large language models can identify risks in a HAZOP with 86% accuracy compared to human experts. I mean, just think about that. They can scan gigantic databases of past incidents and technical documents in seconds, finding patterns that a human team might easily miss.
But, and this is a really, really big but, AI is still just a high-speed assistant. It doesn't have the site-specific context, that gut feeling, or the nuanced critical judgment that an experienced operator or engineer brings to the table. The human team is and will always be the final and most important safety filter.
So let's wrap this all up with the key takeaways. First, HAZOP is the gold standard because it hunts for system deviations, not just broken parts. Second, its real power comes from that structured, team-based approach that uses simple guide words to systematically explore what could go wrong. And finally, while AI is becoming this incredible assistant, human expertise is and will continue to be absolutely critical.
And that leaves us with one last question to chew on. As AI gets better and better at just finding the risks for us, what does the role of the human expert evolve into? What becomes the most critical human skill for ensuring safety in the future? That's definitely something to think about. Thanks for joining me for this explainer.